In this work, we study the problem of active camera localization. The problem of camera localization is to estimate the accurate camera pose in a known environment. The past experiences in this field mainly focus on either direct camera pose estimation via feature matching, or camera pose optimization via scene coordinate regression. Both the above two methods localize the camera in a passive manner, which assumes no control of the camera movement. However, these methods suffer from many challenging scenarios in the real world. For the example of the dynamic test environment and the highly ambiguous regions, where there exist multiple objects that share the same geometry and texture, or the textureless regions. In order to resolve the above issues, a few works focus on camera localization in an active manner, known as active camera localization, where the agent is allowed to move from a bad observation to a novel observation where the camera can be accurately localized. The goal of active localization is to pursue high camera accuracy. To solve this problem, there are three critical questions to ask. How to locate, how to localize the camera for the most accurate camera pose. Where to go, the camera is initialized at an unknown position in the environment, where it should move for accurate active localization. As there are numerous localizable positions in the continuous camera pose space, the problem of active localization becomes highly ambiguous and difficult to solve. When to stop, the agent is unconscious of its ground truth camera pose, hence when it should decide to stop the camera movement. The most existing methods are inspired by Markov localization, which first discretizes the scene map as 2D grids, and updates the discretized belief map by Bayesian filtering with the movement of the camera, where the random strategy, the greedy heuristics, and the policy-based decision are applied to control the action. However, they still suffer from a few drawbacks. The first is that they localize the camera in the discrete pose space. The localization accuracy relies on the predefined resolution of the 2D discrete belief map, such as 40 cm and 90 degrees, which is usually unsatisfactory for many practical applications. Pursuing fine-scale accuracy, such as 5 cm and 5 degrees, would result in significantly increased state space, which is both memory and computation inefficient, and not scalable to large environments and continuous camera pose space. The second is that their camera movement is agnostic to localization-driven scene uncertainty. The past approaches control the actions mainly based on the camera uncertainty, without considering the localization-driven scene uncertainty information much. Scene uncertainty is an intrinsic scene property, which is small for geometry and texture-rich regions, and large for repetitive and textureless regions and other common localization challenges. Scene uncertainty serves as the important guidance for camera movements towards the localizable scene region. To overcome the limitations in the existing approaches, we propose a novel active camera localization algorithm solved by reinforcement learning for accurate camera localization. Our algorithm consists of two functional modules, the passive localization module and the active localization module. The former passive module answers the how to locate question, and estimates the stepwise camera pose in the entire episode in the continuous pose space. The latter active module consists of the scene uncertainty and camera uncertainty components that answer the where to go and when to stop questions separately. The scene uncertainty component aims to guide the camera movement towards the localizable region. The camera uncertainty component determines the adaptive stop condition for the camera movement. During active localization, with the initial RGBD frame, the passive localization module estimates the current camera pose, and the active localization module estimates the next action for camera movement. Such a process is iterated until the active localization module decides to stop the movement, and the final camera pose is chosen as the estimated camera pose at the last step. We evaluate our algorithm on both the synthetic and scanned real-world indoor scenes. To alleviate the difficulty of creating the common localization challenges in the synthetic data, we collect 35 high-quality indoor scenes that feature textureless walls, repetitive pillows, drawings, etc., by design. We use 15 scenes for training and 20 scenes for evaluation. To prepare for the scanned real-world data, we collect 5 indoor scenes from the public Matterport 3D dataset only for evaluation. We also demonstrate the learned intelligent behavior through our algorithm for active visual localization. The top two images are the RGB and depth observations from the agent, and the bottom is the top-down view of the environment. In this case, the agent travels directly to the confident region for accurate camera localization. In this example, the agent emerges the turnaround behavior, which is an efficient solution for this case. For this example, even if the agent initially faces a textureless region, it still intelligently localizes the camera. Here we demonstrate several cases that the agent starts from the same position and generally travels to the same target region. Thank you for watching.